In the world of colors and constraints, where every choice matters and every pattern tells a story, we are challenged to find harmony without repetition. Welcome to the presentation on problem titled Number of Ways to Paint an N by 3 Grid. In this session, we will explore a challenging dynamic programming problem where pattern recognition plays a crucial role. We will carefully understand the problem, derive an optimized solution, and implement it effectively using C++. We are given a grid consisting of n rows and exactly 3 columns. Each cell in this grid must be painted using one and only one color chosen from red, yellow, or green. The key constraint is that no two adjacent cells, whether horizontally or vertically adjacent, may share the same color. Our goal is to calculate the total number of valid ways to paint the entire grid while respecting these constraints. Since the number of ways can be extremely large, the final answer must be returned modulo 10 to the power 9 plus 7. Let us look at the examples provided. When n equals 1, we have only a single row with 3 cells. By carefully counting all valid color combinations that satisfy the adjacent rule, we find that there are 12 valid ways. In the second example, n equals 5000. The output is a large number, over 30 million. This clearly indicates that a brute force or knife solution would be impractical and inefficient. The number of rows n can be as large as 5000, while the number of columns is fixed at 3. Each cell has 3 color choices, which means the total number of raw combinations grows exponentially. Because of these constraints, we must design an algorithm that is both time efficient and space efficient. Instead of focusing on individual cell colors, we make a critical observation. Every valid row of 3 cells can be classified into one of 2 distinct pattern types based on how colors are arranged. This classification allows us to dramatically reduce the number of states we need to track and makes dynamic programming feasible. The first pattern type is called ABA. In this pattern, the first and third cells have the same color, while the middle cell has a different color. For example, red, green, red, or yellow, red, yellow are valid ABA patterns. To count these patterns, we choose one of the 3 colors for the repeating cells and one of the remaining 2 colors for the middle cell. This gives us 6 valid ABA patterns. The second pattern type is ABC. Here all 3 cells have different colors. An example would be red, yellow, green, or green, red, yellow. Since we are arranging 3 distinct colors, the total number of such patterns is 3 factorial, which equals 6. When the grid has only one row, the solution is straightforward. There are 6 ABA patterns and 6 ABC patterns, giving us a total of 12 valid colorings. This serves as the base case for our dynamic programming solution. We now define our dynamic programming states. Let same I represent the number of ways to paint up to row I such that the current row follows an ABA pattern. Similarly, let diff I represent the number of ways to paint up to row I such that the current row follows an ABC pattern. Crucially, the value for row I depends only on row I minus 1. When stacking rows, we must ensure that vertically adjacent cells do not share the same color. From a previous ABA row, there are 3 valid ways to form another ABA row, 2 valid ways to form an ABC row. From a previous ABC row, there are 2 valid ways to form an ABA row and 2 valid ways to form an ABC row. These transition counts are derived by carefully checking colored conflicts column by column. Using the transition rules, we can now write the recurrence relations. The number of ways ending with an ABA row is equal to previous ABA ways multiplied by 3 plus previous ABC ways multiplied by 2. Similarly, the number of ways ending with an ABC row is equal to previous ABA ways multiplied by 2 plus previous ABC ways multiplied by 2. All calculations are performed modulo 10 to the power 9 plus 7. Notice that we do not need to store values for all rows. At any point, only the results from the previous row are required. Therefore, we use 2 variables, same and diff, and update them iteratively. This reduces space complexity to constant space or big O of 1. The algorithm proceeds as follows. First, initialize same and diff to 6 corresponding to the base case. Then for each row from 2 up to n, update these values using the recurrence relations. Finally, return the sum of same and diff modulo the given constraint. The algorithm processes each row exactly once, resulting in a time complexity of big of n. Only two variables are maintained throughout execution, giving a space complexity of big of 1. This makes the solution efficient even for the maximum allowed value of n. This slide shows the complete C++ implementation. The solution initializes the base values, iteratively implies the recurrence relations, and returns the final answer modulo 10 to the power 9 plus 7. The code is clean, readable, and optimized for both time and space. To summarize, we solved a complex grid coloring problem by reducing it to two repeating row patterns. By applying dynamic programming with careful state transitions and space optimization, we achieved an elegant and efficient solution. Thank you for your attention.